In our last example, we used the Taylor error bound to approximate the error in a Taylor polynomial at a specific x value. Another way to use the Taylor polynomial error bound is to approximate the maximum error on an entire interval of x values. So let's have a look. This time we're going to let our function be 1 over x. Our base point is going to be 1. And our order, the order I chose, is 2. And the question we're going to ask is, how big could the error get on the interval from 1/2 to 3/2? Notice the base point is in this interval. If the base point isn't in the interval, then something's wrong. Okay. Well, all of our x values are in this interval. So let's start by writing the Taylor error bound. N is 2. X we don't know this time, but it's in the interval. So let's write second Taylor polynomial at x minus the function at x. Our error bound says that this is definitely less than or equal to m, and we're going to have to find m, over n plus 1. N is 2, so n plus 1 is 3 factorial times x minus the base point is 1, to the n plus first, and n is 2, so n plus 1 is 3. Okay. Now, let's find m. Remember, m is a bound on the n plus first derivative. So let's start taking some derivatives of f. First derivative of f is minus 1 over x squared. Second derivative of f is 2 over x cubed. And then third derivative of f is minus 6 over x to the, sorry, I keep writing x's. These should all be t's. T to the fourth. This should be t. This should be t. Okay. So we have to ask ourselves, to find m, how big does this get on the interval that we're working with, the interval from 1/2 to 3/2? Well, the absolute value of this. So let's see. This is the reciprocal of a power, so this fraction is going to be biggest when the denominator is smallest, and on this interval, it's smallest at 1/2. So the biggest this thing gets is at 1/2. So let's plug in a half. We get 6 over 1/2 to the fourth. 1/2 to the fourth is 16. 6 times 16 is 96, I guess. 96. And I've thrown away the minus sign because we took an absolute value. Okay, so this is 96 is the largest this third derivative gets between 1/2 and 3/2. And so that means that this is m. So m is 96. It's sort of unfortunate that it turns out to be so big, but that's life. Okay, so now we know m. It's 96. Okay, so we can put that in here. It's 96 over 3 factorial times x minus 1 to the third. And 96 over 3 factorial is 16, I think, times x minus 1 to the third. All right, So here's the error bound at x, but remember, all of our x values are in the interval from 1/2 to 3/2. So this absolute value right here, if x is in the interval from 1/2 to 3/2, worst case scenario, how big is this absolute value? In this interval, how far does x get from 1? Well, it only gets 1/2 from 1. So worst case scenario, the absolute value part there is 1/2. All right, and now doing all the arithmetic, 16 times 1/8, that's 2. So the error in the second Taylor polynomial is definitely no bigger than 2. Unfortunately, that's not a very good error bound. I guess that means really you should use a higher order Taylor polynomial than just 2. So now we have two ways of using the Taylor error bound. You can approximate the error at a single point. You can approximate the error on a whole interval. There are a couple other ways that we'll look at next.